Great, we are good to start. Welcome, everybody. And I'm sure you're having a lot of fun on day one. The keynote was amazing. And we have another amazing session lined up for you right here. I am Mohit Juneja. I'm going to be your host for this session. And I've dialed in from San Francisco. Very excited to kind of host you, whichever part of the world you have joined us from. Now, before we start, a quick ask is continue to post your takeaways on LinkedIn, X, tag us so that you and all the community members get all the updates, right? And if you have any questions during the session, we would love your thoughts. Drop your notes, your questions on the engagement, right? So let's talk about this session. I think one question which I hear from almost every single customer that I meet is we have great experiments going on AI in quality assurance, but how do we scale, right? And at Microsoft, the answer has been to pair a scalable automation platform with AI agents that help engineers generate, maintain, and improve tests, right? And that's going to be the core discussion of today's session. So the question on the table is what actually worked when scaling automation across large teams, right? While scaling automation. And where do AI agents genuinely reduce the maintenance load? That's the question on the table. And to answer that, to enlighten us, to give us direction, we have Deepak, Deepak Kamboj. He's a veteran at Microsoft with over 25 plus years experience. He has been a guiding force a lot of teams to adopt Playwright and also build AI-driven test frameworks for various teams who could take his guidance. Right, so he is a hands-on specialist on agentic workflows, MCP servers, and multi-agent systems, and of course, he's a co-pilot champion as well. So please join me in welcoming Deepak, who is going to walk us through on what are the real-world lessons from scaling test automation at Microsoft. Deepak, over to you.
Yeah, thanks, Mohit. Hello, everyone, and thank you for joining this session. And hopefully, you are seeing my screen right.
Perfect.
Yeah. So my name is Deepak Kamboj. So I'm giving a session on real-world lessons which we learn from scaling enterprise test automation with AI agents. So whatsoever I will discuss today comes from a real production systems at large engineering organizations like Microsoft. And this particular pattern applies to any enterprise which is running a large test suites or a shared platforms or a complex CI/CD or a build infrastructure. We will trace the evolution from a manual testing and test scripted framework to a playwright, then AI-assisted development and agents that can plan, generate, diagnose, and propose test repairs. So this is not a futuristic prediction. It's a set of practical enterprise lessons which we learned about architecture, data governance, and adoption. So the goal is to separate genuine AI value from a hype while keeping human engineering judgment at the center or human in the loop. So a quick introduction. I work in a Microsoft Power Platform engineering systems team. I'm building a Playwright frameworks, build infrastructure, and developer productivity tooling for a large engineering organizations. The examples come from production experience, including the approach that worked and approach that did not. So the broader enterprise lesson is that technology alone does not solve scaling challenges. You require architecture, governance, operating culture, data quality, and engineering discipline matter at least as much as the model choice or LLM choice or agent choice for you. So as per the agenda, we will begin with the enterprise scaling wall, why traditional automation fails, and the evolution from a scripted test automation to agent-assisted workflows. Then we will examine the AI agent architecture, including generation, selection, self-healing, and root cause analysis. We will close with governance and guardrails, results and lessons learned, and then means the impacts, pitfalls, any phased adoption roadmap, or finally takeaways. So before we dive into solutions, consider a simple question. Where does your test automation suite break first as and when your organization grows? It may be a maintenance, test maintenance, or it may be a test flakiness, or your pipeline duration, or the test ownership or inconsistent quality standards being implemented. In an enterprise, these are connected system problems, not isolated test problems, which means all these problems related to the overall engineering system you have implemented. So keep your own breaking point in mind as we evaluate where AI can help in solving all these issues. Okay. So traditional automation treats every test as a handwritten script that engineers author and then run and repair whenever a application changes or a UI changes. This slide names five problems which you can see on the right side that show up whenever an enterprise organization grows. High maintenance cost, which means your playwright selectors break with every UI change. So the test suite has to keep on updating every time. There may be a flaky test cases, which means there may be some timeout issues or the race conditions create a particular control or a component unavailable, or there's unreliable results you are getting, or there is a you're eroding a trust in the signal. Okay. There may be a slow creation also, which means now means AI is writing a lot of code for you, and then you will there will be a lot of test cases generated by a agent. So when we were having a manual testing, that test creation was a very slow, which means you have to write a very comprehensive test suites that takes weeks or months. So coverage was always tails the product. Okay. Then for scalability, which means that your effort stays linear. So more coverage always costs proportionally more people, which means if you want to scale your system, you require more people. So, and then limited intelligence, which means your test cannot adapt or self-correct without a human stepping in. If a test case fails, you have to fix it. If your requirement changes, you have to fix it, or you have to update your test case. So there is a human always helping you over there. Okay. So if you see on the left side, these all these three issues means how we are answering them is how we are trying to resolve them. First is means test scripts to intelligence system, which means tests now become generated and these are validated artifacts of a system that reasons, it feels and evolves. So whatever test will be generated by an AI system that will be act as an artifact for a system, and that can provide you all the reasoning, all the healing, and all the evolvements. Okay. Then we are moving from a deterministic playwright system to a adaptive AI agent system where test handles the dynamic UIs also, changing requirements also, unexpected states without human intervention. So adaptive means the authoring part over here. Authoring part will be adapting. The test runner will execute predictable assertions over here. Then from a human driven to a agent driven, where agents can plan, execute, and heal your test cases, which will reduce your manual oversight and rather than removing accountability. So the objective is not to replace automation, it's to cut repetitive works which we are doing, which engineers are doing or a test author team is doing, so that we can have more coverage and that coverage will keep pace with the product change. So if you see how our system evolved from a Selenium to a agents. So this is a five-stage journey which we have gone through. It's just a one enterprise example. It's not a required roadmap for any organization. All the enterprises have their own roadmap, but this is a journey which we have gone through. It began with the minimal test regression alongside the Selenium and Cypress test cases. Then we moved to a playwright on our existing just runner. So the first version of a playwright was not having a test runner, so we have to implement a playwright using a just test runner. Then we moved to a playwright's native test runner for parallelism also, tracing also, and then test pixels also. Then we implemented AI-assisted authoring, where we were using the CodeGen, Playwright CodeGen, and we were using coding assistants like GitHub Copilot to generate our test cases, which were reducing the boilerplate. And then the current stage adds agents and Playwright MCPs. So now Playwright is having a Playwright MCP, we have a Playwright CLI also, and Playwright agents also. So these are used for planning, generation, diagnosis, and any proposed repairing of a test failures. Okay. So the transferable lesson is evolution, not a replacement. Mature enterprise preserve working suites. They always try to keep the existing test suites and they want to deliver control and while introducing each capability behind a measurable gates. So this is our scale problem means we have a monorepo and it's a very big monorepo at enterprise scale. This monorepo or a shared platform has hundred of packages, many applications, and dozen of teams. So a single repo containing hundred of packages, lot of applications which are production applications, and lot of partner teams are working on a single repo. So a single change in a product or a feature, if you want to implement it, cross multiple owners because code, fixes, test, data dependencies, and pipelines all move together. So we have to do a test selection, which means if as a developer I have a one pull request, I want to check that particular pull request. So right now means what was happening means we were running a thousand of test cases for a single change. Okay, so we don't want to go with the same system. Means we want AI maps a code changes to our dependencies and risk, and while team approves that selection rules and release case. Okay, and then test maintenance. Your test case will be become flaky or they become stale over a time. So test maintenance was very costly. It detects fixers or selector drift also and propose focus patches by owners view and implementing change. Then test ownership means we have around 14,000 test cases, so it's difficult to if you are using a Playwright, it's difficult to tell which particular test belongs to which particular team or who is owning that particular test case. If a test case fails, whether I have to create a bug or an incident for a which particular team. So test it uses now code history and coverage data to identify a particular owning team, while named owners accept or read out that particular work. Okay, and then test maintenance, test repairing. It combines all the test logs, all the DOMs, all the screenshots, and any DOM evidence we are getting, which separates a product defect from a test or infrastructure issue. If a particular test case fails, it can be an infra issue, that can be a product bug, or that can be a test bug. So we identify, we do a complete classification whether it's a product bug or test bug or infrastructure bug. Okay. Then scenario coverage or a coverage consistency. If you have a unit test, you can use a code coverage very easily through a particular framework. But if it's a integration test or a web integration test, then getting a scenario coverage is very difficult. So we generate and evaluate tests against shared standards by preserving each product area's context. We properly capture a scenario coverage consistent. We maintain that consistency. Okay. So all these five capabilities reduce repetitive work, but they do not transfer accountability to a single model. Okay, single AI model or a LLM. Okay, the operating principle is very simple. Means in our case, AI proposes, suggests, but human remains accountable. So everything will be under control of a human in this complete system. Okay. Now coming to a second component means a practical enterprise program optimized for four outcomes: faster feedback, stronger test coverage, lower triaging, which means if you have a test failures, there should be lower triage of those test bugs, and then repair cost will be minimum and higher reliability. So if you are running all these test automation in a pipeline, you want a more reliability over there. Okay. So the architecture also needs explicit assumptions also, where means we are using Azure DevOps and GitHub in our case, and we have governed platform that remains the system of record. Okay, so our Azure DevOps and GitHub always remains the system of record, or which we take as a mechanism to identify all the issues. All the execution history is retained, and human approval is mandatory for all the generated changes. Okay, so these constraints make flakiness measurable and every action traceable, which means whatsoever test we are fixing. If any test case is flaky, we are maintaining a telemetry data about that. And whatsoever action we are taking for that particular test to fix, we are maintaining all that telemetry. So whatsoever AI is doing, we are maintaining all that telemetry so that we can use that particular data in the future. So the objective is control augmentation over here, not unsupervised deployment. So now coming to our AI architecture, now we will go through a complete architecture, how low risk, high friction task would you handle to an agent first. Okay, this architecture will be begin by separating a probabilistic reasoning from a deterministic execution. So probabilistic means whenever you are using a AI agents, those are non-deterministic systems. So those will be having a probabilistic reasoning, where LLM will be used for reasoning, and deterministic execution from a Playwright framework. Yeah. So this is a high level architecture. So let's go from a top to a bottom and try to understand different layers. At the top is the reasoning layer. We have a LLM, which can be a Claude 4.8 or which can be your GPT-5. Okay, this particular LLM interprets business intent, plan scenarios, and forms hypotheses when the test fails. Okay, and then means we move down from to a Playwright MCP, which is a browser bridge. Playwright provides a bridge between a browser and AI models. It converts your reasoning into observable actions, navigate, inspect, click, type, etc. It's do all those activities. And then if you go to a second layer, which is a prompt to patch flow, it turns a business requirement into a parse intent. Okay, it provides you a parsing of all the business requirements you are giving, all the prompts you are giving in a native language. Okay, and it do a browser validation. It will generate a test code which will be a part of Playwright MCP action. Then it do a validation and verification of a test case generated. If there will be any test failure, it will do a patching. It will do a auto merging of a pull request, and then it will be a end-to-end system, which will be a from a business requirement. From a prompt, it will do a test generation. It will through a Playwright MCP, and then validation of a test case. If test case fails, it keep going into a loop to a patch particular test case. Okay. Then in the middle is a deterministic Playwright engine, which is actually your Playwright test engine, where we have a three browsers: Chromium, Firefox, and WebKit, and then we have a self-healing mechanism where you can run a test case for a visual AI also, where you can run test for a UI and API also. You can do a API testing also through a Playwright. So that's a Playwright engine layer. And then below that is our reporting and observability layer, which collects all the traces, summarize failures, predict flakiness, and expose coverage gaps. Okay, and it provides a summary in our Teams. Also, you can get a complete digest summary in our Teams or Slack. At the bottom, we have our CI/CD or DevOps layer. So this particular layer selects impacted test cases. It do a sharding using a Playwright sharding mechanism. And now we have intelligent sharding also through our AI agents using the same Playwright concepts. Then it routes a failure. It creates a draft, fixed PRs. So the boundary is essential over here. Here AI recommends and adapts. It provides you a one delivery systems. So all this one delivery system executes, validate, and approve. So this is an end-to-end autonomous testing workflow. So this particular workflow can digest all the PRD's product requirement documents. It can ingest work items. It can ingest any test case written in a Gherkin format or in a YAML format, or you have any collaboration threads going on in an email or a chat, or you have any screenshots or recordings. So this particular workflow will get requirements from all these different systems. And then all those requirements will be given to a planner agent, which combines all this written intent with the application explorer and produce a reviewable markdown test plan. So it will create a test plan in a MD format. Okay. Then we have a generator agent, which converts all these approved test plans into a native Playwright specifications and tests. It creates a fixers, it creates a page object model classes, it creates a test data also, it creates all the utility classes also. If you require a test fixer, it will generate everything for you. Okay. So one CI pipeline will run all these test cases and capture traces, DOM, snapshots, logs, screenshots, and network evidences. If any test case fails, those will be passed to a healer agent, which will propose a focus repair item. And it indicates means there is a change from a change in a particular sandbox, and we have to pay a test case is failing. When we are running a test suite, and we have to auto repair all those failing tests, so it will auto repair all those failing test cases. And this particular will go into a loop to it will miss it from a healer agent. It will be passed to a generator agent. Generator agent will keep on fixing those test cases, and it will run in a CI/CD pipeline. Okay. And at the end, we have our custom AI reporter, which will do all the failure analysis, all the RCA, all it will suggest all the fixes also. and it can send an email also. The complete test result will be sent to you on an email also. So here decomposition matters a lot, means each agent has their own job. Okay, we have a planner, we have a generator, we have a healer, then we have a AI based reporter. So each agent is having their own job, on inspectable output, and one clear failure boundary also. So this is from a business intent how we can go to a green build and we can have a back again. This is full delivery loop for a developer. So we have a 8 steps over here, which starts from a business intent to getting a green merged build. First is a business intent and acceptance, where means we define outcome, risk, guardrails, acceptance criteria. In a second and third step, we generate a product code also from a business intent, and we generate a test plan, and we generate a test cases also. So it generates a complete test scenarios, specification, fixers, and test data along with the complete product code. Okay. And in the fourth step, we review both test product code and test cases, which means artificial intelligent agent check correctness, security coverage, quality, everything will be reviewed before sending to a CI pipeline. Okay. Once product code will be ready, test code will be ready, this and it will be reviewed, it will be sent to a CI pipeline. CI pipeline will be executing everything. It will check any test case test run will be impacted. It will capture all the trace logs, DOM snapshots, accessibility snapshots, all the screenshots. It will do a RCA. It will classify whether a particular failure is a product bug or it is an infra issue or it's a test bug issue. Okay, based on a particular type of classification, whether it's product bug, test bug, or infra issue, it will pass a particular bug or a particular incident to a particular type of agent. For each type of classification, we have a different type of agents. So that particular agent will try to repair a particular bug. So once a particular bug will be repaired, it will be passed to a for a re-review and approval by a human. Once human will approve, that particular PR will be auto merged, and then complete system will be verified. So it's an end-to-end developer loop where we are getting a business requirement, where we are generating a product code, where we are generating a test code, then we are reviewing it, validating it, executing in a build pipelines, doing a classifications, RCA, trying to repair all those issues, and then we are re-reviewing and approving it. Now, we discussed a lot about scenario coverage, means if you have a unit test, we have a code coverage, but what about the integration test scenario coverage? Okay. Coverage is not simply a count of test cases where we a year, okay, means we require a 40 test cases or 50 test cases for a particular feature. Scenario coverage or a coverage is a proof that critical business scenarios still work, which means whatever business scenarios or customer journey we want to validate, all those are working as expected. For that, we require some scenario coverage, and for that, we require some integration test cases to make sure those scenarios, those business scenarios are working properly. Okay. So the engine reads the business change requirements. It go through a change requirements document. It extracts all the testifiable scenarios per business rule and matches all the scenarios to a test specs by intent, not by a file name. Okay. All the unmatched rules become named coverage gaps while the pull request is still open. This reveals silent server-side validation, forgotten errors, and permission branches intent drives, where a legacy test passes into no longer proof the control. So the output is an auditable requirement to test map. So it's a requirement traceability matrix which we generate from a requirement to a design component to a test plan. So it's end-to-end traceability matrix. So this is how means business requirements are converted to a playwright test code. Okay. So generation begins with the Gwanda requirement or a pull request description, not an unconstrained prompt. The agent extracts the affected form, the required field rules, save behavior, all the business requirements that the error be announced to screen reader users. It prefers resilient user-facing locators such as, means we try to use all the Playwright recommended accessibility locators, okay, or built-in locators, for example, get by label or get by load or get by role, okay. And then we assert both visibility and accessibility alert content. We generate a spec, we generate a test data, we generate a testability link, all in isolation. Once the test pass, system draft a PR, and that PR will be given to a human or an engineer to inspect and approve. So it's a, from a business requirements to a playwright test code, how we generate a test from a requirement. Okay, so it's using a proper AI agent which will be going through a business requirement and generating a test code. We are validating a complete test. We do a analysis and then we are create a draft PR, and that PR will be reviewed by a human. This is a very big problem for us. Means we have a 14,000 test cases, and for a small change, a developer is making a small change or fixing a bug, or he wants to implement some feature. So we are running all the test suites earlier, which means we were running a 14,000 test cases for a small change, which means a pull request build pipeline was taking the hours to determine whether a particular test case is passing or failing. Okay. So running every test on every change turns a safety net into a queue and takes a lot of time. For example, for a small code change running more than 1,000 tests. Okay. So risk-based selection were used where we were passing changing modules. We were going through abstract syntax tree. We were identifying differences. So what we are doing now is we are trying to identify which particular test case we should run for a particular code change. We are going through a particular uh, files which are having a code change. We are going through a dependency graph to identify all the dependencies apart this dependencies packages. Not only a package which is getting changed, we are going through all the dependency graph, identifying all the packages which are getting impacted, and we are running test cases against those dependency packages. Not only that, we are also capturing all the failure history, also all the business criticality also. Based on that, we identify a test suites which we should run for a particular pull request change. Okay, so the high risk impacted test runs first with a explicit policy ensuring that code changes path remains covered. So target peer execution is not a replacement for full regression. So we run a full test suites also during a off-peak hours or a release gates, and as a part of a nightly build pipeline also to identify any gaps in an impacted model. So during a pull request, we run a selected test suites, but in a peak of hours, we run the complete 14,000 tests. So what benefits you will get when we are using a intelligent test selection? So what are the benefits when we will be using a smarter test selection? So when we have done this particular pilot project, so all the impact scope the test execution made regression feedback 60% faster, and while keeping all the change parts in the validation set, which means developer were receiving useful signals and test results in a minutes rather than hours. Earlier PR was taking 3 hours to 4 hours. Now we are running a few test cases, which means they are getting a test results sooner in a few minutes. Okay. And then fewer irrelevant execution also, which means a fewer unrelated flakiness, and triage is cleaner. So if you have a few test cases running, which means there will be a few test failures, which will be having a few flaky test cases, which means triaging those failing test cases will be easy and faster and cleaner. Okay. So we treated all these numbers as a pilot evidence, not a universal promise. So even if you want to develop a system where you want to use a smart test selection, you can use these numbers or these type of evidences as a baseline, which will help again optimizing your agents. So we use all these histories, all this telemetry, all these data to optimize our agents. Now, you have test runs. These are running in a particular pipelines, and those test cases are failing. and you require a self-healing mechanism or self-healing architecture where if a test case fails in a build pipeline, you will be getting a auto suggestion to fix a particular test case. Then there should be some agent which will heal or fix those test cases, and then it will generate a pull request for you, and then human can approve that particular pull request. So how we do a self healing? So whenever test run fails, we it's a not a self healing, not a blind retry, or it not even hide your product regressions. Whenever any locator fails or agent pause, we capture the complete trace logs. We capture the accessibility snapshots. We capture screenshots also. We capture trace logs also, and then we compare all those artifacts against the last known good baseline. We call it LKG, last known good baseline, and then we use multiple hypotheses to fix that particular failure. Okay, so we run multiple agents to run a multiple hypotheses to fix a particular failing test case. So that particular agent generates a Git compatible difference. It reruns the affected test case in the isolation. We call it a gauntlet pipeline. Whenever we fix all these test cases, we run in our gauntlet pipeline. We make sure that all these fixers generated by our agents will be running. We run a particular fix multiple times to make sure that that will not be a flaky also. And then means we create a draft PR. That draft PR will be given to a human. Human will review the particular pull request. And then means in an enterprise, in a very big enterprise, identifying a test failure is a very big task. You have to make sure to identify, to classify means whether a particular test failure is actually a test script failure or it's a test bug, or it's or whether a test failure is actually capturing a product issue or it's a product bug, or you are running in some test environment, or that test environment is having some slowness, or there is a network issue, or there is a test infra issue. Okay, so a red test is only a symptom. It's a diagnosis begin with the synchronized evidences, trace logs, screenshots, DOM, console, network logs. Then we do a code difference, test data, execution history. So we have to go through multiple artifacts to identify whether a particular red test is a product regression or a selector drift or a timing issue or an environment issue. So why it's a flaky. Okay. So each hypothesis begin with the evidence, and then we do a comparison to identify, to do a classification, whether it's a test bug, product bug, or a test infra issue. Okay. So we use a classification, we use a confidence score, we use a root cause narrative. Then we try to identify a likely owner also, so that we can assign that particular bug to a particular team or particular team's agent to fix it. Now, we have a smart selection, we have a RCA, we have a classification, we have a self-healing mechanism also. What about the governance and results? Technical capability does not create an enterprise adoption, trust, evidence, and accountability controls. So this brings us to a governance and measurable results, where we get a measurable test results. Okay. So we have a proper governance and safety guardrails because we are using a lot of agents. So we want to make sure that there will be a human in the loop. So all the enterprise governance begins with the human review. So but wherever we are using a AI, wherever we have a AI authored change, which means AI is generating a test case, AI is generating a product code, AI is generating or doing a self-healing or getting a test fix. So everywhere there is a human in the loop, which means engineers review, approve all those AI authored pull requests. Okay. And then means we are giving a least privilege to our agents. We are not giving all the permissions to our agent. We are giving a least privilege to our agents. We always give a read permissions to our agent wherever possible. Okay, so it will be narrow scope draft PR rights we given to our agents. We are not giving any production deployment permissions or authorities to our agents. So always try to give a least privilege to our AI agents and keep a human in the loop. Okay, and then means whatsoever agents are doing, whatsoever action they are performing, all the tasks performed by our agents Agents means even a MCP server, we maintain a telemetry data. We have a proper observability over there. We have proper instrumentation. We maintain all the logs, and we have each requirement ID, prompt version, tool action, model outputs, classifications, approvals. Everything will be auditable. We have a proper data available, which we always track. We always monitor. And then data privacy means whenever anything will be generated by our agents, whether we are generating a test case, we are generating a product code, those will be in isolated environments. So we are not exposing any secrets, network access information, or any uh, customer data or any data also to our agents. Okay, so everything will be in a proper security boundary. We keep our security very essential. We focus more on our security aspects. So we want to make sure that there will not be any environment secrets, any certificates, any network information, any data will be available to our agents. And sandboxing. So sandboxing is very important. Means whenever we are generating any code, any test code, or any test data, or any test plan, all those will be generated in an isolated environment that's not related. Those are not a dev boxes. Those are not a production environments or a test environment. Those are isolated environments just for a sandboxing, and those environments will be used by our agents. So here, transparency, reversibility are what turn our test automation or automation or agents into a trust. So in this particular slide, I'm telling means what were the major pain points and what are the based on our different pilots which we ran and what were the results we got. So in this particular enterprise MVP pilot, uh, test script repair, which we just self-healing, that fell down to a 40%. Manually triaging of our bugs came down to a 30%. Regression feedback was 60% faster now. Bug versus test defect classification reached 90% accuracy. So these are observed pilot results. These are the results from our agents, our automation. Okay, these are not the granted benchmarks which we use. So these are the important outcomes which help us to optimize our agents, optimize our automation. These are not the uh, matrices which we use for our direction of change. These are just the results which we use to identify a risk, to optimize our architecture, to qualify our strategies. So these are results which we use for just for optimizing our agents, not for a benchmarking. So these are the five patterns or real world lessons which we learned. Failure taxonomy. So failure taxonomy first means we want to define it before prompting an agent, which means we want to classify. We want to use a taxonomy. We want to have a measurable triage. So we want to classify each failure, whether that failure is due to a test script, those failure due to a product board, or those are a agent failure or our LLM is hallucinating. So we want to classify everything. Okay. Historical data is very important. Context is very important for whether you want to generate a product code or whether you want to generate a test or you want to fix any failing test case. So failure data, your abstract syntax tree or your accessibility snapshot or your complete context, those are very important for agents to work properly. Okay. And then means we are using a multiple specialized agents. We have a supervised agents and then we have specialized agents. So we are decomposing all the problems into specialized areas, and then our supervisor is assigning those particular problems to our specialized agents. So we are not having a single agent for doing all these activities. We have specialized agents for doing each and every activity. Okay. And then means we are not depending on a single model. We are using abstract model providers, which means we can very easily change models. For each specialization, we can assign a different model based on their activity. We can have a different prompt for each agent also. And then AI is a partner. Okay, we always consider AI as a complement partner. We never want to replace human with the AI agents. Okay, so it's a partner. It's not a black box. We always keep a human in the loop. So, what were the shortcomings or the limitations which were repeatedly damaging our trust? So, do not auto merge AI changes. Okay, whenever AI is generating any pull request, do not auto merge those pull requests. Okay, always have a proper review by a human. Always try to run a particular product code or a test in an isolated environment to validate everything is working fine before checking a particular pull request. Do not build a one monolithic prompt. Have a specialized agents, have a supervisor or a master agent. Each agent should be having their own prompt based on the action or a task they are going to perform. Have a specialized model for a particular agent. Do not have a monolithic prompt and monolithic or a single LLM. Then, as I mentioned, education history is very important. Okay, do not ignore your education history because of particular flakiness and the regression can look identical in one run. Okay, you require a consistent failure to make sure that a particular failure is a genuine failure. There may be a flakiness, it failed once, but it's keep passing after that. So use your education history as a evidence before fixing any flakiness. And do not hard code the model providers in your agents. Try to use a model provider and try to use a multiple models. Okay. And do not launch all the test suites at once. Means we are agents are writing a lot of product code, lot of features, which means we have a lot of code, which means we have a lot of automated test suites. Do not run all those test suites at once. Have a gauntlet pipeline, run those test suites one by one. Okay, and run the gauntlet pipelines or isolation pipelines. Once all those test runs are passing, then promote all those test cases from a from a isolation test to a production ready test cases. So control versus intelligence split. This is very important. Architectural boundary. Playwright is always a deterministic layer. Playwright executes, and agents are always a non-deterministic and probabilistic layer. Okay. So this means the deterministic layer should be a fast, observable, repeatable, and governed by explicit assertions. And probabilistic layer or your agent layer interprets business intents, compares alternatives, it recommends changes, but its output must cross a validation and proper approval boundary. Okay. So whenever you want to define a enterprise roadmap or enterprise architecture, always have a hybrid approach between a deterministic and probabilistic approach. Playwright will be means if you are giving a particular test data and particular test environment to a playwright test given, the test case will always pass. But for a LLM, if you give a same input, there will be a different outputs for a same prompt. Okay, because it's a probabilistic layer. Your agent may hallucinate also. So you have to provide a proper contextual reasoning. You have to provide a proper history, proper context to your agent to make it a more reliable. Okay, so whenever you are want to define your enterprise landscape, try to have a balance between a probabilistic layer and deterministic layer. Now let's turn all these ideas into a phase enterprise roadmap, how you can implement all these different learnings into a proper enterprise multi-phase roadmap. Okay, always have a proper foundation, which means try to use agents, playwright CLIs, and playwright as a baseline. Okay, then have an integration with your build infrastructure, which will be your Azure or pipelines, or that can be a Jira, or that can be a GitHub pipelines. Okay, and then try to implement a AI-based root cause engine or a scenario coverage engine or a classification engine. Okay, where you can able to identify a test failure. You will be able to identify, okay, this particular failure is a product or a test failure, and then you will be able to assign that particular failure to a particular team. Okay, and then try to scale that particular roadmap. Try to have a cross-browser metrics where you can run a test case on the multiple browsers, multiple operating systems, different uh, environments. That can be your test environment, dev environment, preview environment, production environments. Try to scale in a different geographies. Also, for example, you're running a pipeline in a US, West US, or a East US, or a Asian geographies. Okay, then implement flaky detection also over there. Then once that particular system will be able to scale out to a different orgs, try to roll out to a org-wide rollout different stations, and then implement a proper analytics, telemetry, and continuous optimization. Okay. Once everything will be working fine, then you can have a independent measurable human in the loop. So it will be a complete multi-phase implementation along with the human in the loop. So these are the key takeaways, four major takeaways from enterprise platforms and tool chains. Platforms scale teams, shared automation platforms, standard self-service infrastructures. Okay, and then agents cuts your busy work or repetitive work. Value comes from removing the repetitive authoring, maintenance, and first pass triaging. Then data beats bigger model, which means you should be having historical data available, all the test logs, all the screenshots available for a flaky detection, risk scoring, and getting a your confidence score also. Okay. And then governance is the adoption part where means you will be having human in the loop. Okay, you have all the scope will be assessed. You will be having the audit trails. You will be having a telemetry data available. Okay, so define a failure taxonomy first. Have a pilot AI generation on one test suite and then try to extend to a multiple test suites. Have a risk-based test selection strategy. Have a multiple governance gates before scaling. Don't give all the permissions to agents. Run agents in isolation from production and other environments. Yeah, that's all from my side. So these are my credentials.
Fantastic. Thanks a lot for the real world insights, Deepak. You covered a lot of topics: how to really scale automation using agentic capabilities, where to involve a human in the loop, what are the pitfalls. That's a very, very real world on ground situation on how to make agentic capabilities work and get outcomes. Thank you so much once again for joining us on this forum. Deepak, the
Thanks
community
so
would
much.
really benefit a lot from all the insights that you have shared. And to all the audience and all the attendees for the conference, I'm sure this was a huge, huge value add to you. Stay tuned for more such sessions. And as I said, keep sharing your feedback, comments. The community is here to learn from each other, and your comments are really valuable. Thank you so much. Have a great rest of the day at the conference.
Yeah, thank you very much.